Welcome to this explainer. Let's dive right in, because today we're tackling one of the coolest questions in physics. How do we track objects that don't just move in straight, boring lines? I mean, let's be real, life doesn't happen on a straight track, right? Things curve, they soar, they arc through the air. So today, we are going to decode the invisible grid that literally governs the world around us. Here's our roadmap for today. We'll be going beyond the straight line, learning the language of vectors, figuring out how to add and slice those vectors, diving into the physics of a projectile, and finally looking at things moving in circles. Okay, section 1, beyond the straight line. I want you to imagine the physical world around you right now. Almost nothing moves in just a single simple dimension. On the left here, we've got your classic 1D motion. Textbook physics like a stone dropping straight down, or a car just cruising along a perfectly straight road. But on the right, that's our actual 2D reality. A cricket ball soaring out of a bowler's hand, or an airplane navigating the sky. They're moving forward and upward at the exact same time. And honestly, 1D physics just can't handle that kind of complexity. So to decode this 2D reality, we've got to upgrade our tools. We're moving from scalars to vectors. Now scalars, the ones on the left, they just give you a magnitude. It's like knowing a car is doing 60 kilometers per hour. That's great and all, but vectors, on the right, they add direction. Knowing that same car is doing 60 kilometers per hour, but specifically heading north, that completely changes the game. Which brings us to section 2, the language of vectors. Now take a look at this arrow. This is a vector, and it is wonderfully simple once you get the hang of it. The length of the arrow tells you the magnitude, so the quantity, the speed, the force, whatever it is. And the arrowhead, that points the exact direction right toward its destiny. Basically, a longer arrow means more force or speed, and a shorter one means less. Simple as that. But what if we only care about the direction? Well, that is where unit vectors come in. Imagine stripping away all that magnitude, all that size, until you are left with exactly the number 1. That is your unit vector. Think of them as the pure directional compasses of the physics world. We actually use these tiny little letters with little hats on them, like I, J, and K, to mark pure X, Y, and Z directions on our mathematical grid. Okay, so what if we need to reverse course? Turns out, flipping a vector's direction is literally as easy as slapping a negative sign in front of it. Notice how these arrows are identical in size, meaning they have the exact same magnitude, but that negative vector, it points in the complete opposite direction. And to wrap up our vector vocabulary, we've got the position vector. Think of this kind of like opening a map app on your phone. A position vector drops a mathematical pin, drawing a straight arrow from the origin, absolute 0, directly to a specific point in space. It's essentially the universe's way of saying, you are exactly right here. Moving right along to section 3, adding and slicing vectors. So here's a question. What happens when multiple forces pull at the exact same time? Well, ordinary math kind of falls apart. Think about it. If I walk 3 meters north and then 4 meters east, sure, I walked 7 meters total. But how far am I actually from where I started? By placing our vectors head to tail, we get this resultant vector, r, that red line. It acts like a shortcut, completing the triangle and showing you exactly where you end up. This is the triangle law in action. And this builds perfectly into illustrating simultaneous forces with the parallelogram law. Let's say you have two forces, A and B, and they're pulling from the exact same starting point. They essentially act like two adjacent sides of a parallelogram. That resultant vector, r, it becomes the ultimate diagonal compromise, slicing right down the middle between those two competing forces. Now, sometimes we actually need to do the reverse. We need to take a vector and slice it apart. Picture yourself pulling a really heavy lawn roller. When you tug that handle at an angle, you aren't just moving it forward, right? You're actually lifting it slightly off the ground too. So we use a bit of trigonometry to slice that diagonal pull into two clean pieces. The horizontal force pushing it forward, we find that using cosine, and the vertical force lifting it up, which we calculate using sine. All right, let's get into the really fun stuff. Section 4, the physics of a projectile. This is where our vector tools absolutely shine when we're throwing things into the air. You see, a projectile flying through the sky isn't just one messy, complicated motion. It is actually two incredibly simple, totally independent motions happening at the exact same time. Horizontally, it just glides forward at a nice constant speed. Vertically, gravity is constantly accelerating it downwards. And here's the wild part. They do not affect each other at all. Oh, and a quick pro tip. If you ever want to throw something as far as humanly possible, the math definitively proves that a 45-degree angle is your absolute best bet. Okay, let's actually put this to the test with a concrete problem from our source material. Imagine an object is projected at 20 meters per second. It's launched at a 30-degree angle, and we've got gravity pulling down at 10 meters per second squared. The big question is, can we predict its exact future path?
Well, yes, we absolutely can. And honestly, the math here is just beautiful. By slicing up our vectors and plugging them into our formulas, we can see the whole story unfold. We know definitively that the object is going to hang in the air for exactly 2 seconds, we know it'll peak at exactly 5 meters high, and we know it's going to land precisely 34.64 meters away. No guesswork. We are literally using vectors to predict the future. How cool is that?
And that brings us to section 5, moving in circles. Now, motion in a plane isn't just about throwing things, it's also about spinning them. And this introduces a fantastic little paradox. Think about a ceiling fan spinning above you, or even a satellite orbiting the Earth. They are moving at a perfectly constant speed. But here is the crazy part. They are also constantly accelerating. Wait, what? Well, remember, velocity is a vector. So even if the speed stays exactly the same, the direction is changing every single microsecond as it travels around that circle. And that continuous change in direction, that requires an inward pull. We call that centripetal acceleration.
So here we go. This is essentially your ultimate cheat sheet to the universe. We've gone from finding the resultant of competing forces to slicing vectors up with sine and cosine, predicting where projectiles will land, and even measuring the inward pull of a spinning object. We've literally taken the complex, sometimes chaotic reality of two-dimensional motion and translated it into neat, perfectly usable mathematical code.
So I want to leave you with this thought. When you step outside today, try to look for the matrix. When you see a car taking a sharp corner, or a ball arcing across a park, or just a simple spinning wheel, where do you spot those hidden vectors? Because once you really learn this language, you stop just seeing random objects moving around. You actually start seeing the underlying rules of the universe itself. Thanks so much for joining me on this explainer, and keep exploring.